Hello, everybody. I'm Artyom from Octet Labs, and next to me is our speaker, Ashot Vardanian. Who is going to make a presentation about advanced Linux kernel bypass techniques in 2023, and I'm looking forward this presentation very much because I'm very interested in this topic myself because our company is doing something in this area as well. So now I think let's Ashot speak. Передаю слово
Yeah.
Ашоту.
Hello, everybody. Glad to be here. And thanks for introducing me. So, I guess you mostly work on the networking side, and we'll start talking about storage first, but then we'll get into networking as well. So, we'll cover a few topics today. Under this kernel bypass topic, there's like an entire subtopic on existing solutions on top of it. So, like projects like RocksDB, SPDK, UStore and UCall that are developed within my company, and also the lower level technologies. We'll cover all of them. But let me first cover a bit of my background. So it's my third time on CPP Russia. And the two previous times I was here, I talked about GPGPU stuff. So essentially, very compute intensive problems. The second time I was here, I was talking about SIMD programming, so single instruction, multiple data intrinsics, for both x86 and ARM CPUs. It was really fun, and it was like kind of a segue from compute intensive workloads into more kind of memory bound problems because we optimized our solution for the CPUs to a point where we couldn't actually squeeze any more performance from the CPU core. We were just left with a memory bound problem. So the most of my life I spent programming in C-like languages. That's been the case for the last 15 years. I currently run a startup called Unum, and we'll be talking a lot about the technologies we develop internally. I also run the C++ user group of Armenia whenever I'm in Armenia, but right now I'm in San Francisco Bay Area. And as you can imagine, it's the middle of the night over here, and it's my third talk in the last 30 hours. But I'll be as active as possible trying to cover this amazing topic. You can find me as Ash Vardanian on almost every social network, same way as Unum Cloud, our company. But I would suggest you to open up GitHub and look up for those same nicknames. We'll be talking a lot about those repositories. So as I've mentioned, most of the time I spend optimizing the stuff that works and executes on modern CPUs in like 20 nanoseconds. And then I would be finding ways to actually make it run faster, let's say at 30 nanoseconds or 14 nanoseconds. So my homepage or like my browser starting page looks like just a combination of documentation pages for Intel CPUs, for CUDA specification, for LLVM and GCC compilers. But then at some point, you kind of finish with all the low level optimizations. And what you try to do is to assemble an app from all the HPC stuff you've just built. And the app has multiple pieces. Oftentimes, like there is a server involved or like a framework of some sorts, like Qt or Boost or something else. You also need storage. So you need a database that will be storing the data of your application. And at some point, a few years ago, maybe around 4 years ago, I thought, oh, cool. I should try to assemble something out of the pieces that I've previously built within Unum. And I looked at the existing databases. So the story was that the databases were already countless, and every year we just get more and more databases being released. So in the last couple of years, there's been like this rise of startups like Cockroach, like Neo4j, like Tiger Graph and Yugabyte, many of which are built on a project called RocksDB. RocksDB is the go-to solution for an embedded key value store. And essentially, it's just like an associative container. So imagine STD map, but persisted on disk. So whenever you deal with persistent data structures, you end up with latencies, with access latencies that are very high compared to random access memory, which is kind of obvious. So you need to design a custom data structure that would be optimized for external memory. For many, many years, those structures were B trees, but RocksDB is a bit different. It's a log structured merge tree. It brings a few improvements on top of the key value store that everybody probably already knows. It's called level DB. And once RocksDB introduced transactions and multi-collectional databases, companies raced to actually adopt it internally. So Twitter can be a good example. Twitter had their own internal database called Manhattan for a decade now. And it's a public knowledge that in 2017, they decided that they want to replace the underlying key value store with RocksDB. Reason being that RocksDB is relatively fast compared to most other database engines out there. It's also inside a lot of the commercial projects. It's also inside a lot of the Apache projects, even the ones that are not databases, the ones that are just streaming systems. So I thought this project must be amazing, but then I looked under the hood and I found a few things that immediately caught my eye. So some of the most crucial operations within like associative containers would be set and get operations. Whenever you insert a new key value pair or you try to retrieve an existing value for an existing key, and because storage is high latency medium, batch operations are just as important as single entry operations. Because whenever you submit a batch, the underlying engine has the opportunity to reorder the operations and execute them out of order. So the multi-get endpoint uh, just starts with 4 STD vectors being default constructed, which essentially means they will be allocated on heap every single time you call the multi-get function. This may be okay, but then you start digging deeper and realize that the structure of the file that RocksDB built on disk is not really NVMe friendly. So what it means is essentially that the file contains a lot of weird blocks. Navigating through them is not easy. You need complex logic. And whenever there is complex logic involved, it's not that easy to issue tasks at the right time to actually order all of the reads, all of the parsing, decompression, and stuff like that. The last but not the least within RocksDB layer is that uh, being a modern piece of software, it's built on layers upon layers of abstractions. And in programming schools, they teach us that abstractions are great. They help us write nice, maintainable code. But from my practice, it's not always the case. So when you have a lot of layers of abstractions, it takes time for people and users and people who maintain your code to actually understand where the bottlenecks may be coming from. So once you start disassembling those libraries, you realize that just to issue a read operation from disk, there will be 4 layers of function calls. Every one of them will be allocating dozens of structures on the heap. And if we know something about programming low level languages, is that whenever you have like high throughput systems, you have a lot of cores, and all of those cores will be competing for resources. There will be contention on the log. So whenever every one of the cores tries to allocate some memory, there's some shared heap data structure that they will be all trying to log, which will never be fast, or at least fast enough for us. So uh, with this, the problems with the RocksDB layer kind of stop, but then we end up with problems below it at the Linux layer. So this is a chunk of code out of the ext4 file system implementation within Linux, which is probably the default go-to file system on most modern systems. What you immediately see is a ton of if statements, and it's already suspicious coming from high performance computing background. But then you start building diagrams of how the IO is being funneled within the system. So most of the applications will be just using libc function calls to read or write data from disk. They will be pulling data from user space buffers most of the time. But this data will be coming from page caches, and into those page caches, it will be coming from block IO layer, which will be served from the device layer. So this is too many layers, and if every one of them contains a temporal copy, it means way too much will have to be synchronized. So in our case, we oftentimes deal with projects or like with hardware setups where we have up to 24 NVMe SSDs within a single machine. Every one of those NVMe SSDs is capable of 1.5 million operations per second. And we have two sockets of CPUs, every one of the CPUs with 64 cores. So you end up synchronizing 128 physical cores and 256 logical threads to actually squeeze out all of the performance available through the NVMe drives. And whenever you have to build up like temporal copies for every one of those layers, you lose half of your performance. So essentially, on a modern machine, you can squeeze 200 gigabytes per second worth of read throughput from your NVMe SSDs, but more realistically, 120. And if you just benchmark the throughput of the memory system on dual socket 16 channel DDR4, uh, you end up with a setup that is only 120 gigabytes per second and realistic throughput. So all those numbers may not make too much sense for you right now, but imagine that to build up a really fast database that we ended up doing internally, you need to build up a concurrent in-memory hash table or mem table, or often in many cases a skip list that will be storing your data in large chunks until it's big enough to dump on disk. You also need a versioning and a garbage collection mechanism, which is called compactions in databases. But most importantly, you will need an IO logic, and you need it fast enough. So when we think about IO logic on modern computers and we focus on storage for now, there is the classic Unix IO system calls that everyone knows. Then there is a POSIX interface that's been adopted by Linux since early 2000s, since 2002, the kernel version 2.4, sorry, 2.5. The next one is IO Uring, which is considered fresh and modern. So I think we started adopting it in probably late 2019. It's available since kernel version 5.1. It's now the go-to way of doing kernel bypass on modern systems. But then there are like three more opportunities that most people are not really familiar with. One of those is Magnum IO, which is the effort on NVIDIA's side. They have a way for you to map data from SSDs into the GPU video random access memory, bypassing the CPU. So it's not exactly the classic kernel bypass, but it has the same logic. The two other projects, SPDK and DPDK, are essentially brothers. SPDK is designed for storage, and DPDK is designed for networking. Their idea is relatively simple. Instead of issuing system calls or even just using some shared ring buffers, like in IOU ring, to exchange tasks with the CPU or like with the Linux, uh, instead, let's create a user space driver that would be essentially part of the user space application. And whenever you're dealing with SPDK, it's nice to think that any other process actually has no access to the drives that you are working with. It's not really the case, but it's a nice way of thinking about it. So the reason why SPDK appeared is that at some point, Intel and Micron have been working on really low latency hardware, more specifically the 3D point. They announced it back in 2015. The latency is sub 5 microseconds. And those Optane drives are partly discontinued, but some of them are still on the market. And they are capable of well over 1.5 million operations per second, even with a single drive. The problem with those low level libraries and low level interfaces, as always, is how verbose they are. So a few years ago, with my first talk at CPP Russia, I was covering GPU programming techniques, and there was this library called Vulkan, sorry, a framework or an interface called Vulkan, I should say, because it's more of a standard. And whenever you look at Hello World applications for Vulkan, I may not even be able to remember how many lines of code were in such projects. This would easily be over 1,000 lines of code just for a Hello World, potentially even 2,000 lines of code. SPDK is similarly complex. So the Hello World application referenced on the website is close to 500 lines of code. To run it, at least in the past, until the more recent releases, you actually had to have root privileges because you end up changing the configuration of your system and detaching and unmounting your SSDs, mounting them into your user space application. The second step within your program, aside from having root privileges as a prerequisite, would be to probe for NVMe controllers. So essentially, you're searching for all available endpoints of NVMe devices. And then you have to manually allocate your non-thread safe IO queues for every one of the controllers. And this is like one of those places where you need a lot of knobs to control how efficient the IO will be happening. So from our experience, it's oftentimes beneficial to have, let's say, 3 separate queues for every one of your high performance drives. Point number 4 is that all of your memory that you allocate will have to be page aligned. There is a trick that SPDK uses beneath the way they kind of exchange data with the drivers. It's dependent on allocating huge pages on Linux. And this puts additional constraints on how this memory should be allocated. But this is nitpicking, and we should not go as deep into the details. The points number 5 and 6 are kind of obvious. So if you've ever used AIO on Linux or on POSIX systems, you know that you would submit the requests and then you poll until you get the completion notice. So a few things to remember. Once you take SPDK, you have to immediately forget about the file system. So SPDK gives you access to the raw block device. So essentially, if you have a 4 terabyte SSD, this means that you will be having 1 billion 4 kilobyte size pages that you cannot address byte by byte. And you can only write into like various chunks and parts of this disk without explicit understanding of a specific file ordering within this drive. So all of the logic of designing a file system is essentially on the application designer. Second part, which is probably obvious, and I would recommend it not just for SPDK, but also for IO is to forget about page caching within Linux. So IO also allows you to work with ODirect file descriptors. Essentially, those are the files that are opened with an ODirect flag. It instructs the operating system to avoid caching of data. And the benefit, of course, is that whenever you have congestion within your system, you will not be facing the evil key swap D process. So that process is responsible for managing the swap space. Uh, the caching can be, of course, very helpful if you are dealing with small files. But if you're working with tens of terabytes of data on a machine that has at least 10 times less RAM, the problem is that kswap D will be the bottleneck for every one of your threads on your computer. And your CPU utilization of the single process will be 100%. And all of your real worker threads within the application, within the above database layers, will be just stagnating. But it's not a big deal for C++ developers, I guess. Every one of us has developed at least one cache within our careers. So if you need a cache, you can always write one. And reflecting back on the file system part, I've already mentioned that we are not getting any explicit structure for the ordering of the files, but we also don't get byte addressable memory. So all of the operations within the SPDK API are designed for blocks, for 4 kilobyte pages most of the time. Now let's put some numbers into the picture. So before we get into tables and comparisons of various IO methods, I should probably introduce our CPU, which is a Threadripper in this case. It's based on Zen 2 architecture from a few years back. The CPU has 64 cores and 128 threads, We used DDR4 memory with theoretical throughput of 204 gigabytes per second, but more realistically, it's closer to 120 gigabytes per second, as mentioned. And we had about 64 terabytes of NVMe storage, some of the fastest SSDs on Earth. Those ones are not Optane, these ones are Samsung with higher capacity. And last but not the least, we also had 4 NVIDIA GPUs in this machine, and our database engine had and still has GPU acceleration, so those things come handy. So if you just take Unix I/O mechanism and you take those super high-end, fast, and fleshy SSDs, you only squeeze 50,000 operations per second out of a drive that is capable of 1.4 million. With POSIX AIO, which was designed and introduced over 20 years ago, so it's definitely a very familiar interface. You can already get a 10x performance improvement, actually 11x, up to 573,000 operations per second out of the same drive. Next, we have IO Uring, which is the most recent standard interface within Linux. On average, we get close to 900,000 operations per second on a single drive. But what's important here is that benchmarks should not be done in vacuum. So it's one thing to benchmark your application on one thread for 10 seconds and call it a day, but it's completely different setup when you're running on a beefy server with dozens of cores, with a dozen SSDs, and you end up with all kinds of bottlenecks across your database, across the underlying operating system layers. So what we observed with IO Uring is that it has far better horizontal scaling than all the previous interfaces. So things like Unix IO and POSIX AIO, they depend on system calls. IO Uring allows you to avoid system calls if your operations are frequent enough. So if you do not have to do system calls, you have to do less synchronization. And with 8 SSDs, we reach 5 million operations per second, which is quite remarkable considering that most databases generally operate at the performance levels of tens of thousands of operations or hundreds of thousands of operations. Here we're working with millions. And now, probably the pinnacle of the story, SPDK. Last year, we've reached 1.2 million operations per second out of every single one of the SSDs, totaling at close to 9 million operations per second across 8 SSDs within a single node. So, assuming linear scaling with 24 SSDs on our future setups, we expect to get close to 25 to 30 million operations per second. So you might be asking, like, what kind of operations are those? Like, how lightweight this is? Well, there is a benchmark that is called Yahoo Cloud Serving Benchmark. It's the default, actually, one of the two default benchmarks for databases. One other is called TCPH or TPCH. It's like more focused on transactional workloads. Well, this is more for CRUD operations, and CRUD stands for create, read, update, and delete. So we've actually forked this benchmark. It was originally in Java, and we rewrote it into C++. It's entirely open source. You can find it on our GitHub under UCSB, which stands for Unbranded Cloud Serving Benchmark. So essentially, we took away the Yahoo part and we made it available to everyone for much broader use cases. And one thing that was lacking in the original benchmark is the random batch operations. So the databases and the database engines of the past all depended on synchronous IO, and all of them performed like one operation at a time. But in modern realities, people work with batches most of the time, so it makes sense to benchmark those. We took RocksDB and we took UDisk, which is our internal key value store. So in the previous slides, we compared different IO mechanisms. Now we see how a choice of IO mechanism translates into your performance, your application's performance in the above layers. So with RocksDB, the batch writes are averaging at about 57,000 operations per second. For UDisk, that's 320,000 operations per second. And for batch read operations, the difference is even larger. So it's not a 5.8x improvement, it's 6.5x performance improvement. So within this benchmark, we're dealing with a collection of data that is 10 terabytes in size, and we only have 1 terabyte of RAM. So this is not achieved through caching. This is achieved purely thanks to I/O optimizations. And just to provide more validity to those numbers, a single benchmark like this takes a few days to run on a piece of hardware that costs like a proper sports car. So those numbers have been averaged over millions of cycles. So we thought it's a nice accomplishment. So how can we distribute it and how people can use it? So we've built up one more open source library, and I'm actually super excited to share some of those fully open source things. Because in the last years, when I was talking about technology, I had nothing to share. All of our stuff was proprietary, but in the last couple of years, we've released a ton of really cool things, many of which come with kernel bypass tricks. So this piece of software called uStore is essentially our open source database layer. It has similar logic to how Redis is built. So Redis is a database built on top of a key value store. In their case, it's an in-memory distributed key value store. And in our case, we focus mostly on persistent single node setups, and oftentimes embedded instead of a standalone application. So we thought if you have a fast associative container like std map, you can serialize all kinds of data like graphs and documents and vectors into it. And moreover, once you have a nice API, you can build up high level wrappers on top of it. So overall, we thought, okay, we have this vision, how we achieve it. Sadly, it meant going away from pure C++ world, more towards like C and C++ setups. So a lot of the high level languages that we want to be accessible for our users do not really work very well with C++, especially when you build up large applications. So we standardized a C99 layer on top of all of those different modality implementations like graphs and documents. And on top of this C99 layer, we've actually implemented yet another layer of C++, or alternatively, a Java interface, a Python interface, a Golang interface, and so on. So this project essentially aims to be the BLAS of create, read, update, delete operations, a narrow, slim C-layer interface for all things data. So the way it looks is like this. Uh, it's relatively trivial. So for every operation, we have a function, let's say like UKV write, and there is also a data type like UKV write T, which kind of defines all the available properties of this operation. And it also has one neat trick that seems like a forgotten art of programming, which is strides. A stride is essentially a step that you need to take in order to access the next entry. So there's always this question of how do we pass an array of arrays from one language boundary into the other? Because every language runtime implements arrays in a different way, and passing arrays of arrays without copies is very tricky. So strides is the way to do it. And I think this is one of the first cases where it's employed within databases instead of numerical libraries. Even though C++ is the core topic of the conversation, I think it's also relevant to notice that whenever we C++ developers build our libraries, we oftentimes build up frameworks. We want them to be the foundations for the future of infrastructure. So there's this project called Apache Arrow, which is essentially copyless representation, or I would say it's an array structure representation that tries to help developers avoid copies of data whenever they pass them from one language runtime to the other. All of our database interfaces are compatible with Apache Arrow, and we've built up a Python layer on top of it, which looks like Pandas and Network X. Pandas for tabular collections and Network X for graph-like collections. So it's super easy to use. But this story of kernel bypass is not specific to storage. In the last year, we've also dealt a lot with networking problems. And the recent changes in IOURang came super handy. So about a month ago, or maybe like 2 months ago, I saw a bunch of new additions to the Linux kernel 5.19. Uh, Most notably, multi-shot operations and managed fixed files. The idea is that whenever we build up networking stacks, we have this decision to make. Are we building a TCP IP oriented networking stack or networking library, or a UDP oriented system? We internally love UDP, but it essentially boils down to building up your internal tools and your internal protocols. Most of the internet is still operating on top of REST API, on top of JSON RPC or gRPC, and all of those things are built on top of TCP/IP stack. TCP/IP requires stateful connections. Whenever you have a stateful connection, you have to generate a new file descriptor for every connection that you accept on your socket. And in the past, because you didn't have this like managed fixed files pools ability within IOUring, managing stateful TCP/IP connections with IOUring couldn't be as fast as it is now. So there are two endpoints that you can use within liburing. Liburing is a high-level wrapper on top of the IOUring system calls. Those would be IOUring prep accept direct, which is an endpoint that invites new connections on the socket. And another one is for you to register a sparse list of file descriptors. And I used those two to build up a networking library for JSON RPC. But before I dive into this library, let me mention one more really cool feature. It's the NVMe pass-through. So essentially, even though IOUring is a very efficient approach to asynchronous IO in modern systems, it still has to translate your requests to the underlying storage driver or networking driver in this case, or in some cases. The optimization that was added in 5.19 allows larger operation structures, operation describing structures, as big as 128 bytes, if I'm not mistaken, or it could have been 128 bits actually. So still, I definitely remember that that was like a 2x size improvement compared to the previous size of operations handled by IOUring. It essentially means that you can immediately encode NVMe operation codes and submit them into IOUring, avoiding the need for SPDK altogether. But back to networking, we've built up this tiny library. It's called ucall, and it's just a couple thousand lines of code. It's super easy to read and reason about. It was my attempt to take a very lightweight networking approach and IO approach, which is IOUring, and a bunch of libraries, all of which are SIMD accelerated. So SIMD against stands for single instruction multiple data, meaning that those libraries are really well tuned to process more than one piece of data within a single CPU cycle. And when you're working with networking packets, you have a few operations that you need to make. One of those operations is whenever you receive an HTTP package, message, whatever, you need to split up the HTTP headers from the rest of the text, from the payload, and you can use SIMD accelerated libraries for that. Then, whenever you parse those headers, you have to infer some metadata. You can use SIMD accelerator libraries for that as well. But then, within the payload, if you're working with a JSON RPC model, you have a JSON object. This JSON object I decided to parse with a library that every one of you probably already knows. It's called SimJSON. It's really neat, and it uses all kinds of assembly tricks for AVX 512, AVX2, ARM Neon, and a bunch of other different instruction sets, and the results were absolutely remarkable. So I started with Python, and I had this library that everyone loved. It was called Fast API. It has fast in its name, so you'd expect it would perform really well. But when I took my laptop, which is an 8-core Core i9 MacBook, I ran a piece of software and I received a latency close to 6 milliseconds. and both the server and the client were running on the same machine. And 6 milliseconds to me is more of a latency of accessing a nearby country, let alone talking from one application on the on the same machine to another application. But then I took a commodity machine on the cloud to make this more replicable, because you never know what's running on somebody's laptop. And in my case, I took the C7G instances on AWS. Those are based on ARM Graviton 3 chips. So those are really energy efficient. I run Fast API again. I got a latency of 1.2 milliseconds and a grand total of 3,000 requests per second handled by a single threaded server, which may be okay if the rest of your application operates at only 2,000 requests per second. So this wouldn't be a bottleneck, but in every other case, it is a problem. So, for comparison, if you use gRPC and you produce a server in Python, uh, it will perform 10,000 operations per second. And then the library that we developed in the C layer performs 230,000 requests per second on a single CPU core. And once you wrap it for Python, it looks almost exactly the same as Fast API, equally easy to use. Just 5 lines of code to build up a Python server. It of course gets slower because you need to allocate a few objects for every single function call, but it's still 210,000 requests per second. So all in all, just in a couple of days of work, using the right I/O mechanism and a set of good open source libraries, we've reduced the latency of a Python application by a factor of 30 to 55, and we've increased the throughput by a factor of 70 to 77x. So this is huge. And most importantly, this library is open source, also available for commercial use cases as well. Go check it out. It's called ucall. And sometimes when you speak about the latency and the throughput, people start complaining about potential problems with your bandwidth and some other sacrifices that you had to make. And a couple of times when we posted the results, people immediately came back to us requesting the numbers for throughput as well. So throughput would be the total amount of data that can flow through the socket um, whenever you build this kind of application. So those numbers are really fresh. I requested the team to prepare them specifically for this talk. So if you have tiny packets, 1 kilobyte in size, which is below the maximum transmission unit, so the message will not be sliced, you will be getting a throughput close to 300 megabytes per second on a single CPU core. With 4 kilobyte messages that will be split up into potentially 3 chunks, you get up to 900 megabytes per second. And I'm pretty sure there is still room for optimization, but this is already way higher than most other open source libraries can provide. So we've talked about I/O a bunch, and we've talked about databases, which is I/O bound in terms of storage. We talked about networking, and we have different kind of I/O bound there. But there's also I/O bound within random access memory. So we can kind of translate some of the problems uh, into this like IO bound terminology. So whenever you benchmark an application with something like perf, it will tell you how many of the CPU cycles were stalled. And if it says that a lot of the backend cycles were stalled, it generally comes from two reasons. One of the reasons is that you're using very heavy operations that take a long time to expire. So, really heavy seamed assembly instructions can be the case. A more common case, though, is that you're working in a memory bound domain and the CPU finishes executing its lightweight operations and it waits for data to come in for the next lightweight operations. So one of the things that I was building recently for open source is vector search engine called usearch. It's a super hot topic these days, and I've built up a tiny C++11 library that is super compatible. It has bindings for Python, JavaScript, Rust, and Java. Those are the first four ones that I implemented. which kind of really positions C++ as a really nice language to design high performance abstractions, but also give it away for languages and runtimes that do not have such an explicit control over memory. And then today I've added bindings for Objective C and Swift. Somebody on our team also added bindings for Wolfram, and a friend of mine is adding bindings for Golang. So this is like a super portable data structure. What usearch is an index for nearest neighbor search in high-dimensional vector spaces. This topic relates to AI, and because of like all of the AI bonanza that is happening in the last few months, people are searching for new vector search libraries as well. But my first intuition, if I were to start working on a vector search library coming from an HPC background, would have been to optimize the distance functions to use seamed assembly. But it's not the case. This problem is not compute bound, it's more of a memory bound problem. And most of the time, when you're working with this kind of distance functions, uh, those operations are really easy to parallelize. They're like element wise operations, like the dot product. So, with the right pragmas, your compiler can generate decent assembly. So, you don't have to write the assembly here, but you have to understand the prefetching mechanisms on modern CPUs and modern operating systems. So if you look at modern vector search libraries like Faiz by Facebook, they will have a lot of prefetch intrinsics within them, which is a common approach to actually prefetching the memory. The problem with it is that it almost never works. So half of the libraries that I saw with this kind of intrinsic in them, I can just comment out this lines with prefetch, run the program again, and it will work just as well. With GCC, there's an alternative to like Intel or x86 specific intrinsic, which is built-in prefetch. It's kind of similar to how SIMD intrinsics are both present in hardware specific and compiler agnostic manner, but they're also present in an inverted manner where they're compiler specific and hardware agnostic, like in GCC's case. In case of vector search, there's vector search in memory, but there's also vector search in persistent memory. So once you start working with really large collections, it's all about optimizing your access patterns within external memory. And in there, there's like this system called madvice, which some of you are probably familiar with, but this is one of the rare system calls that few people use. Luckily, within IO there's also uh, an operation code for madvice, which allows you to prefetch certain parts of memory from disk to achieve better performance. I do not have exact numbers for prefetching over here yet, but they will be available within the repository next week. Though I have some numbers to give you an intuition on how fast this thing runs. So, assuming this is an IO bound problem, depending on the kind of memory that you use in your machine, you'll be having drastically different numbers. The numbers here are obtained for, again, C7G instances with DDR5 8-channel memory and of really high frequency, above 4 gigahertz. If you take the servers that I've just mentioned with Zen 2 CPUs, like the ones over here on this nice pictures, even though this CPU is liquid cooled and has 2 times the number of threads than the CPU over here, because it uses DDR4 memory, instead of having 100,000 operations per second, I'd be only having 30,000 operations per second on a seemingly more powerful CPU. And once you get into external memory, the difference in the numbers becomes even more drastic. So, with this, I want to sum up. We've covered 3 really interesting topics. One of them is about uStore and the database that we're building with kernel bypass techniques with SPDK and IO Uring. The second one is about networking and the newest features within IO Uring for multi-shot calls. It's the ucall library. You can also find it on GitHub. The last one is the most obscure, potentially the most trendy, showing how vector search and a lot of memory bound problems are also a special case of IO bound. And depending on what kind of memory you're working on, you may again use either prefetching techniques within the compiler, within compiler specific tools, or alternatively, you can again use IOUring to advise the operating system to prefetch specific buffers ahead of time. Um, I also want to add that we have some Python packages, but probably more importantly, as I've mentioned, I run the user group for C++ in Armenia. We have a lovely community of over 700 developers now. We organize meetups from time to time, and we're always looking for great speakers. We've had a lot of guests from Russia in the last couple of months, or last couple of years, I should say, and we'd be really happy to host you as well if you're ever coming. So drop me a line. And with this, I want to finalize the talk. Thank you. Do we have any questions?
Yes, thank you very much for your very interesting talk. And it seems like we have some time for questions, for public questions, and we have two questions from our participants. The first one is whether you use any kind of file system in your solution, or is it purely direct disk access?
So if you can run directly on block device, you can obviously also run on a file system. So we have both approaches available. We oftentimes benchmark on common file systems like XT4 that I've just mentioned. So you do not even need like a high performance file system to get to the numbers like the ones that I'm claiming.
But you don't have any file system layer of your own, right? You rely on
Oh, of,
kernel in the.
oh, of course, we have like our own file system layer, but we do not abstract it as a file system per se. So there is no like a virtual file system interface for it that we could have registered within the kernel. So essentially, the file system layer is fused with a database. It's just internal logic of how we allocate persistent memory within the block device.
Uh, uh, Now, the second question is, how does UDisk compares to AeroDisk? I'm not
Iris Spike.
sure. Aerospike, yeah, right.
Uh,
You should know
uh,
better.
so, so R Spike, it's weird that somebody's asking it because, like, I've heard that name yesterday again, and someone was also wondering if it relates to us in one way or another. I'm not sure if they have like their own key value store or if it's a persistent on disk key value store, and if they use any kernel bypass. Generally, this is not what we compare with. We compare most of the time with things like LevelsDB and RocksDB, and sometimes other ideas that are published in papers and may have not been implemented in code yet. And I can see the third question as well, which is coming from Dennis again. Can you please elaborate on the relation of TCP to IOUring? So, IOUring is a broad interface for anything related uh, to the operating system and communicating with it. So essentially, the whole idea of IOUring is to do system calls without system calls. So, like, how do you request the operating system to do something without introducing an interrupt, a thread switch, a context switch? And in pursuit of this vision, people behind IOUring have been adding new and new operation codes over time. And those operation codes slowly extend the capabilities of IOUring into new domains. Those would be first storage, then let's say networking. And within networking, there is no specific distinction uh, or a specific marker saying that IOUing applies specifically to TCP. IOUring applies to both TCP and to UDP, and you would actually get even more performance improvement if you're using it for UDP. It's just that in our case, we thought that the most recent features within IOUring are really nice to implement a broadly compatible TCP IP oriented library. So that's why we applied it here. I hope it answers the question.
So, uh, uh, if I may, we seems to have some more time. If I may, I have some questions of my own. First of all, Mm, SPDK is basically a block layer. It doesn't have any file system in it, but it has something called blobfs, which is some strange beast intermediate between key value and real file system. Have you any experience with it? Because for me, it's kind of a puzzle why it exists in the first head. Mm,
That's a great question. I had the same puzzle in my head when I was looking for documentation. So I thought it would be really cool to try and benchmark it. But then all of a sudden, like working with SPDK is so complicated that we ended up using the bare bones, most fundamental layer of SPDK and never touching all of those like key value abstractions that were proposed within the broader standard.
Okay, and also a second tiny question regarding your UCall library. Have you tried benchmarking it with really small requests, like some closer to the minimum possible Ethernet frame? Because when we are talking about low latency, 1 kilobyte is like an infinity, and
Yes,
you have
sure. 100%. So this numbers that I had, let me find them. Sorry. This numbers 230,000 requests per second. The size of the packet here is essentially 8 bytes. So what's happening here is that we built up an endpoint called sum, which is basically just summing up two numbers. It receives two 32-bit integers and it returns another 32-bit integer. So this is about as small of a packet as it can be.
okay. Thank you very much. And
You're welcome.
now I think let me invite everybody who is interested to participate uh, in our discussion, which is to follow. And thank you all very much for your time. Thank you, Ashot, and goodbye to everybody.
Bye bye, everyone. Thank you for joining.